Welcome to the Explainer. We hear the term machine learning thrown around constantly these days, right? But today, we're actually going to map out this incredible territory to understand how these systems truly process information and make decisions. We're popping the hood and breaking down the foundational paradigms that make the whole thing work.
Let's jump right in by asking the fundamental question that started this whole field. What does it really mean for a computer to learn from experience without us programming every single explicit step? Think about it. In traditional programming, we give a computer the rules and the data, and it spits out the answers. But in this new paradigm, it's totally flipped. We give the computer the data and the answers, and it has to figure out the rules for itself.
And really, that brings us to our formal definition. Machine learning is basically a specialized field of artificial intelligence, where models learn from data to improve their performance over time. They engage in what we call predictive modeling, meaning they try to forecast outcomes without being explicitly programmed for that specific task. Essentially, we're giving these systems the ability to discover patterns, find hidden relationships, and make decisions autonomously, based entirely on the data they ingest. It's pretty amazing.
Here is our roadmap for today's explainer. First, an intro to machine learning. Second, supervised learning algorithms. Third, unsupervised learning algorithms. Fourth, reinforcement learning algorithms. And finally, we'll wrap up by comparing the approaches.
Okay, moving to part 2, supervised learning algorithms, the guided path.
So supervised learning is built entirely on labeled data. Think of it like a student studying with a complete answer key right next to them. Every single piece of input data comes with the correct output attached. This setup generally tackles two main tasks. First up is classification, where the model predicts a discrete category. A classic example? Looking at an email and flagging it as either spam or not spam. The second is regression. We use this when the output is continuous, meaning the task is to predict exact numerical values, like trying to forecast house prices based on square footage. To solve these specific problems, data scientists rely on a few foundational algorithms. You've got decision trees, which learn through a branching process of elimination. There's support vector machines, or SVMs, which find clear boundaries to separate different classes of data. Then you have linear and logistic regression, which rely on mathematical trends, and of course, naive Bayes, which operates purely on probability. All of these heavyweight algorithms heavily rely on known inputs and desired outputs to train the model.
To really visualize linear regression in action, just picture our data points plotted out on a graph. The algorithm calculates the mathematical line of best fit through all that noise. By establishing this specific mathematical relationship from our labeled training data, the model can now confidently predict future values for any net new data we happen to throw at it.
But here's the catch. How do we know if the model is actually any good? Well, you have to compare its predicted values against actual reality. Look, a mathematically perfect model would have all its predictions landing directly on a flawless diagonal line. But since no model is absolutely perfect, we have to look at the residuals. That's just a fancy term for the exact mathematical difference between the prediction and reality. Analyzing these errors is exactly how data scientists fine-tune the entire system.
Let's shift gears to Section 3, Unsupervised Learning Algorithms, the Explorer. Now, in this paradigm, the data has absolutely zero labels. None. The algorithm is tasked with identifying patterns entirely on its own without any answer key to help it along. Imagine I hand you a chaotic, messy box of mixed screws, nails, and bolts. Nobody handed you a label for every single piece, but you naturally, almost automatically, start grouping similar shapes and sizes together. You look at their physical features and just organize them. Well, that is exactly what unsupervised learning does with massive datasets. And that instinct brings us directly to clustering, which is the primary application of unsupervised learning. The objective here is to group similar data points together based entirely on their inherent features. The goal isn't to predict a known target, mostly because we don't even have one, but rather to discover underlying structures, segments, and hidden relationships buried deep within the data itself. The famous k-means clustering algorithm actually handles this mathematically in a few very specific steps. First off, it randomly places cluster centers and assigns data points to the nearest one. Second, it calculates the true average of those assigned points and literally moves the cluster center to that exact mathematical spot. Finally, it just repeats the process. It assigns points, updates the center, and iterates. It keeps doing this until those centers finally stop moving, a state data scientists call convergence. Beyond clustering, there's another massive area for unsupervised models: dimensionality reduction. Imagine you have a dataset with hundreds of incredibly complex variables. Algorithms like principal component analysis, or PCA, act kind of like a compressor. They reduce that massive, unwieldy feature space into just a few meaningful visual axes, all while retaining the essential structure. For even more complex data, like high-res images, we use autoencoders. These are neural networks that compress input down through a bottleneck and then reconstruct it. It is literally a brilliant way to simplify data without losing its soul.
Moving right along to Section 4, Reinforcement Learning Algorithms, the gamer. So, if supervised learning is studying with an answer key and unsupervised learning is organizing a messy room, reinforcement learning is basically playing a video game. What if there is no pre-existing data set to study at all? Think of a robot trying to navigate a physical maze. It has no historical data to reference, so how on earth does it learn to find the exit? It learns by interacting with its surroundings, making choices, and directly experiencing the consequences of those choices.
To pull this off, the system uses a formal framework called the Markov Decision Process, or MDP. It breaks down into a few key components. You have the agent, which is the learner actually making the decisions. You have the environment that it operates in. You have the actions the agent chooses to take. And crucially, you have rewards. Rewards are the feedback evaluating the success of the action. The agent learns purely from this ongoing system of rewards and penalties, desperately trying to maximize its long-term score.
Two of the most famous algorithms here are Q-learning and SARSA. They both use mathematical formulas to iteratively update the value of different choices, but they approach it from slightly different angles. Q-learning is what we call an off-policy algorithm. It looks optimistically at the absolute maximum hypothetical reward of the next step. SARSA, on the other hand, is an on-policy algorithm. It updates its strategy based strictly on the actual actions it is currently taking. But ultimately, both of them are constantly balancing the exploration of new paths with the exploitation of known safe rewards.
Which brings us to Section 5, comparing the approaches, the grand finale.
When we actually stack these up side by side, the fundamental differences jump right out at you. Just look at the input data. Supervised requires all your data to be labeled. Unsupervised requires exactly 0 labels, and reinforcement, it starts with no predefined data at all, just an environment. Because of this, their end goals shift drastically. Supervised wants to calculate very specific known outcomes. Unsupervised wants to discover underlying structural patterns, and reinforcement wants to learn a series of optimal actions to maximize a reward over time. And out in the real world, this is where it gets really cool. You'll see supervised learning algorithms like decision trees used for predicting stock market prices or recognizing images. You'll see unsupervised models like K-means deployed for clustering customer segments or detecting weird anomalies like credit card fraud. And you'll see reinforcement learning models powering highly dynamic tasks like beating humans at chess or navigating self-driving cars through busy city streets.
So I'm going to leave you with this final thought and question. Which learning path is going to solve your next big data challenge? Because whether you need to accurately predict the future, discover hidden structures in the chaos, or navigate totally complex, changing environments, understanding these 3 fundamental paradigms is the absolute key to unlocking the true power of your data. Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.